So indeed, today I wanted to share with you some views on how to decarbonize metallurgical processes. In case we run out of time, I want you to go home with the outcome of the presentation. The idea is that we think that sulfidation and sulfur have a key role in order to unlock the recovery of metals. And you will see that we have some scalable reactors technology that we believe can generate value where there are no other competitions. And as you may know, the challenge of decarbonization is pretty hefty, and therefore it's important to have some solutions or some hope. Ultimately, the last bullet point is about the carbon-free metal production. I will use carbon-free with quotes everywhere. We can argue or discuss later on what it means. But we know that if we were to switch to sulfide chemistry, we would actually be able to get easier access to carbon-free reduction. And indeed, why would we think about decarbonizing metallurgy? We talk a lot about iron and steel because it's a major materials. But actually, iron and steel is one of the lowest emissions material per ton of steel. The challenge with steel is we consume a lot of it, but the CO2 emissions are not very high. And if you think about a sustainable future and electrified future, you will need more and more of all the elements that I've listed here. And they are not elements, they are metals. That's the name of those things like copper, aluminum, nickel. And then you go in more exotic elements like tellurium or perhaps rare earth. And here I've put a range of emissions because, there's a way to do accounting, and depending on the country or the energy sources and so on and so forth, you may happily sit at 7 tons of CO2 per ton of nickel, or you may be facing something like 100 tons. So you would have to decide if this is acceptable and not, which is not my forte. But the important thing is that where does this impact come from? It's written here, it comes mostly from the sourcing, the supply, and the transformation of the raw materials into semi-finished products. And that's where you're going to start to see this coming into your supply chain. The issue that we are facing is not only these obvious environmental challenges, but also the productivity. The production rate and the purity of the semi-finished products that you're finding today has never been seen before on Earth. What is accomplished by this industry is exceptional, either to make very high purity metals or very high purity inorganic compounds like the one you would be using in the battery technology. And the productivity that comes with it is quite remarkable. It's very hard to illustrate productivity in one slide, but I'm going to try. This is a typical one plant size. So for each of those metals, you imagine there are perhaps between 15 and 100 or 200 plants around the world who are all doing this at a rate of thousands of tons per year. But actually, for iron, it is 4 million tons per year. That's one plant that is delivering iron to the specification. And for other metals, you may say, well, it's much different. Well, it's still pretty significant for nickel, right? 60,000 tons of nickel per year is quite an impressive number. 1,000 tons per year is 100 kilograms per hour. Okay, so you can imagine how many people per hour can come to the stage. That's equivalent to the amount of metal coming out when you do 1,000 tons per year. And they're not doing thousands, they're doing thousands of thousands. And interestingly enough, despite this truth across the board of high productivity, there is a chemical metallurgy behind those plants which is extremely different. And I've tried to highlight it here, but it's inherited from the ores that are used and the inherent chemistry that comes with the ores that are used. And here is an illustration for iron. So we all know what's the product. The product is steel, which is an alloy with less than 1% of things in it, perhaps manganese, perhaps other elements. But it starts from this. It starts from what we call an oxide, which is a compound of iron and oxygen. That compound for iron is quite particular, because it's made of 65% per weight of iron and 35% of oxygen. So the challenge of the steel makers is to get this and remove the oxygen. Whereas if you think about aluminum, for example, the feedstock is called alumina, aluminum oxide, a compound of aluminum and oxygen, but that compound is only 54% aluminum. So now the challenge is to get rid of 46% of oxygen per ton of feed that is coming through the plant, and the product of the aluminum smelter is not an alloy of aluminum. It's pure aluminum, 4 nines, 5 nines. And then you can go on and on. It's a fascinating journey if you want to learn about it. But of course, copper and non-ferrous metals mostly come from sulfides or mixed sulfides and oxides. That means you have different challenges than what you would have for steel or with aluminum. For example, the ore of copper is called chalcopyrite, and this is almost 50-50 copper and iron. Right? So the copper business, which is buying copper feeds, is actually buying 33% of iron every time they're buying copper ores. Now, the challenge is no longer the same from a chemical standpoint because now you have sulfur instead of having oxygen. So we have natural evidence that perhaps this situation is more favorable energetically from a CO2 standpoint and so forth than perhaps the iron situation or aluminum situation. And I will not go into the details into that. I'm happy to discuss at a later stage. Now, the supply chain challenge has led to the productivity that I mentioned, the consumptions that I mentioned, the CO2 emissions, but we have to acknowledge also the low value added along the supply chain, which means that incremental solutions are unlikely to mitigate the challenge of the environmental impact that we are looking and facing. Perhaps you could do that, but most probably you would have to decrease the standards of the purity of the metals that you would be making. And it's very difficult to illustrate this again, but I'm going to try. So on the x-axis here, you have the content in the valuable things, the valuable metal that you would be selling. So if you're doing steel, you have here the ore, and here you have the steel products, which is almost 100% iron. On the way, you have two terms that you need to remember from your supply chain. One is concentrate. A concentrate is like a concentrated version of an ore. And the final version is a compound, which you may know if you do any chemistry in your operations. This is pretty familiar. Compounds are usually around 50 to 60% metal. Concentrate are here, and ores are here. And you can see that depending on which metal you're looking at, I'm going to highlight here aluminum, the value added changes drastically. Perhaps you know that aluminum oxide is a commodity. You can go to a ceramic shop today and you can buy aluminum oxide. It's pretty cheap. It's $300 per ton. But aluminum itself, as you may have noticed in the LME, London Metal Exchange, is very high. I'm using a very conservative number of $2,000 here, but I think it's much higher right now. Anyway, you can see that the step of going from the concentrate or alumina to aluminum metal has a value added that is comparable, even perhaps higher. Per ton of metal, right, because this is important, that's what you care about for society, per ton of metal you have this type of reality. This reality is very different for iron, it's very different for manganese, very different from chromium, titanium, you go on and on. Each of those metals have those value chains that don't make a lot of sense to innovate either here if you don't innovate here or the other way around. Now, the other way to illustrate this challenge is to look at the capital expenditure for this supply chain, as well as the environmental impact. So now I'm flipping the axis. The metal that we had before is located here. Here is the compound, here is the concentrate, here is your ore, because now I'm looking at the problem the other way around. I'm saying that the challenge of a mining company is to take care of the other metals. And I'm saying that the challenge of a smelting company or a reduction company is to take care of the other things that makes the compound. What I mean here is that this is metal oxide, all right? This is the alumina that I talked about. The role of the reduction or smelting operation is to get to aluminum. But along the way between the the ore and the compound, you have to handle everything else that nature has given with it, which is mostly other metals. So I'm not going to talk too much about this. This is very well documented. This is actually pretty exciting developments that are happening about how to make steel without CO2, how to make aluminum without CO2. We can talk about that later on. But I want to talk about the upstream. I want to talk about how do we get to compounds today. And this is done today by a sequence of processes which have a process technology bottleneck. These steps, again, I'm not going to perhaps spend too long, but this is called grinding and physical separation. That's the typical mills that you're seeing in a mine. Cracking is a little bit of high temperature reaction to allow certain things to happen. Leaching is when you start to get in trouble, because leaching means you're going to use a solvent, most of the time water, so an acidic solution or a very basic solution, and suddenly you're moving from a solid processing to a water-based processing. And as soon as you do that, suddenly the density changes. Suddenly you have the density of water, you have limited dissolution, and therefore it's very difficult to leach. Assuming you can leach, basically you have dissolved the whole solid. Then you go into what we call solvent extraction, which is now invoking different solvents, meaning water versus non-water solvent, and trying to find a way to use that type of chemistry. Now, what I said before is the capex and the environmental impact is what's interesting. Now, while as you go through the entire supply chain, you are kind of linearly removing the other elements, which means you're increasing your concentration. You can see that your capex curve in red here is not linear at all. You can see that there is much more capex in the solvent extraction step, hydrometallurgy in particular, versus the minerals processing, which is kind of solids that you're moving around, that you're crushing, and kind of separating physically. And then if you compare the global warming potential, you can see that it scales the same way as the capital expenditure. Now, it's not the same number, but the point being is that the trajectory is the same. The most harmful and the most challenging from a capex perspective operation is the solvent extraction, which explains why today, in a world where we want to double the production of nickel and separate from cobalt, everybody looks around and say, okay, are you going to do the investment? No, I'm not going to do it because it exists already and there's enough capacity elsewhere. So suddenly you will always be dependent on whoever owns that facility in order to see the metal coming out, but you're going to be facing the global warming potential of those technologies. And that's where we're trying to investigate and innovate by going from directions that have been practiced in the past, but a little bit forgotten by the Western world industry. The first one is what we're trying to do is to stay with solids as long as possible. The reasons for using solids is particularly that because it's dense matter, and therefore you're handling less kilograms or volume as you're trying to get the metal. And there are not millions of ways you can, for example, increase the recovery of the valuable elements from your ore or your concentrate. You have to increase what we call liberation size. Here are different ways you do that. Short story, you're going to have to use temperature. Second thing you can do is you can use different physical properties of the minerals and the phases that you have along your supply chain. Here is an example of the density difference between sulfides, which are lighter than oxides, but you may also know that these have different magnetic properties, which means you can use magnets to kind of concentrate and separate certain phases. Both of these point to using sulfur chemistry. But you would also want to use sulfur chemistry for the notion of selectivity. And selectivity is a very important concept in chemistry. I have here a very things that I'm happy to discuss. But this is a chemical series of, on the right side, you have the oxides. So the oxides are kind of the one that you know about corrosion. So copper is more noble than iron, which itself is more noble than aluminum. And silver is one of the most noble metals, like gold. So that's what you would see here. At the top, you have silver. At the bottom, you have aluminum, and also some of the radioactive elements. But if you were to switch oxygen for sulfur, suddenly the sequence that I described is upside down. Suddenly, aluminum, which is a very difficult metal to make from an oxide, becomes mid-range. It's difficult to see, but aluminum is sitting here. Suddenly, nickel is one of the most noble metal as a sulfide that you can think of, and the radioactive elements actually also went up, leaving behind a new sequence at the bottom of the sulfide series. Copper, which was more noble than iron as an oxide, is now sitting below iron. So you can imagine that not only do we change the sequence through which we can selectively react certain metals than others, but we can also play around the relative difference of position, which is also changing, even though it's difficult to see at that scale. Therefore, we think we can use this idea of selective sulfidation because we know that sulfur will have a very different reactivity than carbon, than hydrogen, than solvents, than anything you can think about because of this reactivity that I talked. Now, the last thing that we can do, and it goes back to using high temperature, is we can perhaps partially melt. Or perhaps we can gasify certain of the elements that are coming in your feedstock, which allows you now to handle a gas-solid reaction or gas-liquid reaction, which is something we know pretty well from chemistry. Finally, which was a little bit hinted at this chemical series, if you were to use sulfide, you could think of different reduction technology. You could use of carbon-free metal production, and why I would do that? Because, well, there's a cross here, but the current paradigm in metal extraction is to start from an oxide. So M is the metal, O is the oxygen. What you do usually is you try to concentrate the metal, and therefore you need a place to put oxygen. And usually the place where you put oxygen is a hydrocarbon. Either carbon or hydrogen or whatever you want, but basically at some point you need to remove the oxygen, and we do that in a gas phase. Well, you can see immediately that this is never going to be carbon-free as soon as carbon is involved, or if you do use other type of hydrocarbon. But think of the other chemistry. If I was substituting oxygen for sulfur, suddenly I would have a metal sulfide, which means that if I do the decomposition, the only thing I have to do is to remove the sulfur. There is no carbon in that equation. The only thing that I'm carrying around is sulfur, which is actually an element that we know pretty much how to work with. And here is an example of liquid copper, which was made through this reaction. So now it's solidified copper, but it was liquid. You can see the shape of the dome that we're finding. This was done by electrowinning of sulfides, and I'll show more about that in a minute. So that's why in 2021, after quite a lot of work, we published a paper which was accepted in the journal Nature, which kind of explained how the sulfidation and sulfur chemistry might open up all of these very important practical industrial parameters like recovery and selectivity, which ultimately scale with the environmental impact of your process per ton of metal that you're making. But of course, the challenge becomes, all the typical questions, which are, well, does it scale? Is it compatible with an existing infrastructure? Will it actually lead to less emission and OPEX and CAPEX? Will it actually allow carbon reduction technologies, which is the thing that we've been investigating? So I'm going to show you a highlight of some of those answers, and then I'll be happy to share papers or other things for that. So the prior art in sulfidation is very optimistic from a purely engineering standpoint. Reactors have been made at the size of almost 500,000 tons per year. You have a picture here, and you can tell it was a long time ago because it's a black and white picture. The idea here is, of course, if you have a mixed metal oxide, let's say two metals together, nickel and cobalt, what you're trying to do, or manganese, what you're trying to do is you try to selectively combine sulfur with one of them, and then you want to leave the other one as an oxide, because you're really only interested in the metal sulfide. Now, of course, you have to manage the SO2 and S2, which is pretty well done today in the catalyst industry, for example, for regeneration. The previous attempts were using different sources of sulfur. They were using sources of sulfur that are not selective, either because there was iron or hydrogen or carbon. In our case, we're using elemental sulfur, S2. Now, the challenge, of course, is most of the kinetic and thermodynamic information are not available, but the good news is if you have them, then you can scale and design your reactor. And finally, there is a very important point about energy. This reaction is exothermic. It means that it's generating more energy than it needs, and therefore it's kind of a self-autothermal reaction where you don't need extra energy to maintain the temperature of your reactor. As a matter of fact, it's quite the opposite. Usually you have to cool down your gas. Now, here is one of the versions of the flow sheets that we've been proposing. The short description is, here is the core of the sulfidation reactor. This is the technology we developed that we master. And then all the other things are existing unit operations that you have in an existing metal processing or any gas-solid reaction plant. This is to make the nitrogen. This is to manage the sulfur and SO2 that are coming out of the reactor. And then what is even more important for us is at the end of this, you get your mixture of oxide and sulfide, where the sulfide were formed, and then you can do physical separation. You can grind and use magnetic separation. You can grind and do physical separation in order to get the metal sulfide and the metal oxide. Again, you have all the information needed in the paper, but of course one of the questions is what is the operating expenditure per ton of feed that would go in the flow sheet that I just showed you. Now, this will be very dependent on the scale. There is a law of scalability. This is 10,000 tons per year, 100,000 tons per year, perhaps 1 million tons per year. Of course, the OPEX goes down as you go larger in scale, but even an OPEX at $300 per ton of feed, when you talk about certain markets where it's $2,000 or $3,000 for a concentrate, are not out of the reality. Why is it so inexpensive? Because it's an exothermic process. We don't need to buy a lot of energy to run those reactors. What are we consuming? Sulfur. Perhaps some of you know that sulfur is a commodity. Certain countries like the USA, the value of sulfur is very low. We have excess capacity of sulfur, same in Canada. Now, certain countries of the world don't have sulfur and buy sulfur as a commodity at a price that is very, very cheap per ton of sulfur. There is an underusage of sulfur today in our society. Now, the other things that you might start to say is, how about the CO2 emission and sulfur dioxide emission? Again, we've compared here a conventional hydrometallurgical method to separate two elements, which has an equivalent CO2 impact between 10 and 100. And on the other hand, our sulfidation technology, I mean, depending on what scale you're at and so on and so forth, is going to at least reduce by almost an order of magnitude the CO2 emission, because we don't have a lot of energy consumption and there is no carbon or hydrocarbon or water consumption. Now, once you have this metal sulfide in hand, as I said, you can do the reduction without CO2 emission. So here is a tiny example of, it's a tiny, it's a 50 grams example, 100 grams example of a spontaneous decomposition of metal sulfide. No carbon, no hydrogen. What you need here is just to reach the temperature and pull the vacuum in the system. And what you see coming out here is the elemental sulfur that we put in at the beginning to make the metal sulfide. And what is left behind is your metal out of the spontaneous decomposition that happened at high temperature. So this is, in that case, there was an induction furnace that was used, but you can use other type of reactors as much as you need in order to do the decomposition if you reach the temperature. This is a liquid-gas reaction. In the gas phase, you're going to collect any impurities as well as the elemental sulfur that you put in at the beginning. What's left at the bottom is a liquid alloy or a liquid metal that you can cast and therefore do your conventional metallurgy. The other example that I mentioned before is the direct electrolysis. Here is an example of 1 kilogram capacity reactor that we built and run at MIT that does the electrolysis of copper sulfide or any sulfide to liquid metal, in that case liquid copper, and then evolve elemental sulfur as a gas due to the electrolysis process. This was done in the context of copper extraction, where we also were able to make iron in a separate step. So I apologize, the picture is here. This is when it runs with iron, we make liquid iron, and when it runs with copper, we make liquid copper. Oh, here is the final version of the iron sulfide electrolysis, which would lead again to liquid iron and elemental sulfur gas that would come out of the reactor at the top. Now, we have worked extensively on this. I personally have spent 10 years working on sulfide and sulfidation, and therefore we have accumulated a lot of knowledge about practical deployment of that technology. And it's, I don't have time to show all of these examples that we worked on, but perhaps you are recognizing some of the challenges that your companies or organization are interested in. For example, battery material separation, perhaps the recovery of certain of the byproducts of the copper industry. Very recently, we have shown very good results on tantalum and e-waste processing in general, which contain a mix of the silver, the copper, and of course the tantalum for the capacitor. We have also some very interesting results on sulfide electrolysis for silver, gold, and platinum group elements electro-refining. Some of you may have visited this facility that are using cyanide or chlorides, which are kind of very difficult to implement right now, especially in the USA. So we have a good advantage here because we're using a very safe sulfide-based chemistry. The good news here is that all of these are available at large scale. With the support of the Department of Energy and currently the DoD, we have developed large-scale reactor. This is a 2-kilogram capacity sulfidation reactor. And then on the right side, you have the electrolysis reactor that supported the copper work that I was talking about. So we are ready to work with anyone who's interested in changing the way we get access to metal. This is my last slide, take home. It's possible to have a holistic view of the supply chain and find breakthrough transformation. We think one of them is going to be the sulfur-based chemistry, which allows not only to a better selectivity, but also supports the reduction technology that I mentioned, which don't have any carbon, don't require hydrogen economy to be existing. These are based on existing reactors and capability, and altogether we think that the sulfide chemistry might help greatly the improvement of the environmental impact of metal extraction. And with this, I'll entertain your questions. Thank you.
Thank you, Professor Allanore. That's really great. What a compelling new idea this is. A couple of questions about this. I think they're related to operations and scalability and CapEx. So first is, what types of CapEx investment do you think is required for these processes to move ahead? Yeah, the way we did the CapEx investment, and by the way, this is available in the paper, we made a comparison with the incumbent technology. And solvent extraction is defined by the selectivity of your solvent. And you may know that the solvents are never 100% selective, which means you have to have many operations of recirculation. And in our case, we're using a selectivity that is at least twice better than any of the solvent extraction existing technology. And the CapEx scales immediately with the selectivity. A higher selectivity means your CapEx decreases drastically. And we are in this situation of reducing the capital investment compared to incumbent or existing technologies. Okay, well, that's promising. Okay. Let's see, do you need to be concerned with sulfur emissions in this case, in the sulfidation process? So sulfur is actually managed already, and sulfur emissions don't exist. What we mean is sulfur dioxide. And you've seen that sometimes you have a little bit of sulfur dioxide that is emitted. Well, you may know that there are very well-established technology to capture that sulfur dioxide. And one of the ways to capture it is to make sulfuric acid. So some of you may have already known that the sulfur emissions have been decreased drastically from SO2 or sulfur-containing technology thanks to this abatement. And our CapEx includes the cost of managing these emissions so that they don't come out to the environment, but they are kept in the smelter. Okay. And another question, we hear a lot about carbon-free steel, obviously. Are you getting traction? What's industry feedback so far on your sulfidation process? Yes, so there is the non-ferrous, so non-ferrous means non-steel, right? Non-iron. The non-ferrous industry is a little bit slow to go back to the game of new technology. The reason being that there are not that many players outside of China, which means there's a little bit of, pardon the word, ignorance about where do nickel come from, where do cobalt come from, what are the emissions related to that. Of course, there's a big challenge of the battery technologies, which requires both metal, so we don't want to speak too loud about saying, hey, how are you going to get your nickel and cobalt if you have environmental impact for the processing of these materials? Does it alleviate the battery benefits, and so on and so forth? So I think we are a little bit, the industry is a little bit shy right now in addressing these challenges at the core because society hasn't picked up yet on how much emissions and water impact and whatnot comes with the supply chain. But we hear about it, especially I think Europe is particularly
is particularly talking about those challenges of how we're going to get the cobalt to make those batteries and so on and so forth. So, it's picking up, but it's true that it's not as big as carbon and steel, just because of the sheer size. The sheer numbers don't really compare. One is 1 billion ton, the other is like hundreds of million ton.
So next for you, you say you're in the lab right now, you say it's kilogram scale production you have. So the next step would be, in scaling up, would be, what would be the next step in scaling up? Are you looking for industry partners or certain type of pilot?
Yes, so we have an ongoing techno-economic evaluation to try to understand exactly what you're saying. At what stage does an industry can take off that technology to be the owner of the pilot development and so on and so forth, versus other metals for which we have already a scale that is kind of competing with any players, including in the US. I will cite the example of rare earth metal, which, as you know, are very important for magnets. There is no rare earth metal producer in the US at a scale of more than perhaps 500 kilograms. So in our case, in our lab, we've already made some alloys that are beating anyone in the US in terms of capability. And therefore, because the list is enormous, right, we have 15 elements, perhaps 7 different markets, the strategy to figure out which one is ready for the next stage of pilot demonstration versus the one that needs a little bit more refining with the existing players to really understand where do we fit and how do we success is what we're doing right now. And we're doing this mostly by a commercialization exercise. So I have a student who's probably going to reach out to you in order to discuss how does it fit and how it could be valuable outside of MIT.
Great. Okay. That's a great send-off for us. Thank you so much.
Yeah, thank you.